But I notice when I look at this something that seems a little bit strange. If you're familiar with mathematics, if you're familiar with different graphing functions, it looks like, yeah, at first glance, maybe that is a line, but if we kind of zoom out and look at it more closely, it looks like maybe it is just beginning to curve a little bit. That if we had taken a little bit more data, maybe it would have started to flatten out and curve some. So I want to ask the question now, could this data fit a curve? Instead of a straight line, y is proportional to or equals mx plus b, is there a curve that could fit here? So to test whether or not there was a curve that could fit, I first manipulated the data. I said, okay, let's see how the x values are related to y squared. We know that the x values are pretty closely related to just the y values in and of themselves without any changes made to them. That's what we saw down here with these really good r values. It made a very good line of best fit. But like I said, I saw some curving pattern here. So I'm going to do something called linearizing the data. I'm going to see if I can make an even better line by manipulating the data sum. So instead of seeing if x is proportional to y, I'm going to see if x is proportional to y squared. So you can see here that I have taken all my y values and I've told the computer to find the squares of them. And so I'm going to get a brand new graph that looks like this. These purple lines here, let me take the green ones off. Now what's interesting, if we compare the purple, which is the y squared, to the green, which is the y1, of course it's very different because the purple shows the square result. Just by glancing at it, pretty interesting, you can almost see that the purple seems to make a much straighter line, while the green, we can see it really does look like it's flattening out a bit. So this is interesting. This is a process known as linearizing the data, and until you're really good at mathematics and physics and can figure some things out, sometimes it's just a hit or miss, trial and error type thing. So this was my hit or miss. I just asked myself the question creatively, thinking outside the box. Okay, x is proportional to y, but is x proportional to y squared? Does that give me an even better line? And again, I kind of knew to do that because my original green data points were a little bit curvy. So in my new line, I'm going to test that out. Now I'm saying, okay, these y values, how are they proportional to the x values? And you can see here that that is a pretty dang good line of best fit right there through those purple data points, my y squared versus my x's. The r statistics for this are much closer to 1 compared to my last one's 0.989 compared to 0.99, 0.994 compared to 0.996. So even though it is just a tiny bit of a difference, I would say that this is a better fit. Squaring those y values is indeed a much better fit. And we still have the m value here. That's the slope of this. So my y values squared are proportional to m times the x values plus the y-intercept. And that y-intercept, I think we can all agree, it looks like it's a pretty tiny number. That line hits the y-axis so closely to 0 that we could probably effectively get rid of that and call that a 0. Now, I know you guys are kind of confused about the mathematical manipulations I'm doing. And it seems like I'm kind of going above and beyond our original question. Remember, our question was, what variable can we affect to change the period of a pendulum? And I think everyone will agree that we ultimately found that, oh, okay, increasing length of the string increases the period of the pendulum. And we could be satisfied with that. But we're trying to go deeper. We're trying to be more mathematical, more precise, more scientific about it. Is there a way that we can model that relationship mathematically and use that to predict what the period would be at a certain string length? Let's say that we're designing a pendulum for some reason, maybe for a clock, maybe for a piece of artwork, maybe for some engineering design. And we want to predict what is the period of this pendulum going to be if the string length is 2 meters. So how can we do that? Well, I guess we could kind of guess and see that, oh, okay, my last data point was here, so maybe 2 meters will be right about here, and have a period of about 3.5 or something. Well, that's not quite going to cut it. We want something very precise, something mathematical, a tool, mathematical tool that will help us make predictions and really solidify this relationship. Yeah, the string length increases and the period increases, but how? What's that relationship like? How can we model it? That's what all this graphing and manipulation work that I've done is all about. Here's my x and y values. There's the line there. Here's my um, x and y squared values, and there's the line for that. That line is the best fit that I have. Okay, so let me start with that, and I can start to model this mathematically. So let's just go right off of these purple data points, and let's start writing this down and seeing if we can make some sense of it. The y values were the period squared, so I've written that down right here. Capital T is period squared equals m. That's my 4.177 number, so I've written that down. Times the x values. Well, what was graphed on the x-axis? The string length, the length of the string, right here. So I'm going to use a capital L for that. And then we could say plus the b value, the y-intercept. Where does this line hit the axis? And that's such a small number that I can effectively call that 0 and not even have it in my equation. Also, think about what that number would mean. That number would mean the period squared when the length is 0. When my x values, when my string length is 0, what is the period going to be? It's got to be 0. 0. If you don't have any string, if your string length is 0, you're not going to have an oscillating pendulum. You're not going to have a pendulum system to analyze. So, of course, my y-intercept value should be 0. So I'm left with this. All right, that's kind of interesting. Can we do anything with this? Well, yeah, we can do lots of things with this now. We can use this mathematical model as a prediction tool. We can plug in a number there for L and run this equation, and it will tell us the period squared of that pendulum with that length of string. So now we have really answered the question and really solidified the relationship. What is the relationship between the length of the string and the period of a pendulum? And using some graphing analysis, using some linearization by squaring the y values, we have found this pretty good, pretty solid mathematical relationship. And we have the raw data, the evidence to back it up. So we've done a lot. We've asked a question. We have formed some hypotheses. We rejected 2 hypotheses. We accepted 1 hypothesis. And so now we can make a claim. How can we change the period of a pendulum system? We can change it by lengthening or shortening the string, by changing the string length. Okay, do we have evidence for that claim? Can we justify that claim? Well, yeah, here's our data. Here's us plotting the data. We squared those values. We got a really great line. We know there's a relationship there, and we can even model it mathematically. So experimentation is all about obtaining data to answer a question, to test a hypothesis, one independent variable at a time, and to try to find relationships between variables, using some graphing skills to come up with a mathematical model. Now, we can even do some interesting things with this equation. You'll see that up here I have the equation that we derived from our experimentation. And down here, this is the famed equation that relates the period of a pendulum to the string length using some fancy math. The scientists who discovered this equation did just what we did, taking data, using mathematical manipulation. These scientists are a little bit more creative and knowledgeable than us, though, and they recognize some other things that deals with harmonic motion and forces, the force of gravity, stuff like this. And they found pi, and they found what we call little g, which is, some of you may know, the acceleration due to the Earth's gravity. acceleration due to gravity on Earth. That's what little g is, and that number is 9.8 meters per second squared. So this is a standard value. This value does not change at the surface of the Earth, um, relatively speaking. So if this is known, we can, and this is constant and this is constant, we can actually take our equation here and see how well it reflects this by maybe calculating little g from our equation. So tied into the experiment that we've done, tied into this little equation that we've made, it's possible to find the acceleration due to gravity on the Earth and compare it to the actual value. So let's do that. I'm actually going to start with this equation down here, and I'm going to make it look a little bit more like ours. I think that'll be easier since we just have one number out here. So first of all, we can notice the difference between these two equations, that this one has a t squared on the left side, and this one has a square root on the right side. So how can we get them to match? Well, why don't we take this whole thing and square it. Why not? If we take that whole thing and square it, we're going to get a t squared on the left side equals, we have to square the 4, that's 4, or excuse me, square the 2, that's 4. We have to square the pi, that's going to be pi squared. And then we have to square this thing. Hopefully you know that a square root squared just gets rid of the square root. So that's going to be L over G, and I can write it like that. So I'm trying to see if my equation contains little g like this one does. So what I'm going to do now is take the two parts of my equation that I can kind of pull out and say are the same and set them equal to each other. I'm trying to just have little g as a variable to see what our equation claims is the acceleration due to the Earth's gravity. So this equation has the form t squared equals a constant times L. And this equation has t squared equals a constant times L. So I could pull out both of my constants. Sorry about all the arrows here. And set them equal to each other. And that is going to make g, little g, as my only variable. Okay, so you can see that I've set these equal to each other, this constant and this constant right here. And now little g is my only unknown variable, and I can do a mathematical trick where if I have an unknown in the denominator, I can bring it up over here and swap it out with that. So I'm going to get little g equals 4 pi squared over 4.177. And then I can solve for little g. 9.45. Now remember what little g is actually supposed to be. It's the acceleration due to the Earth's gravitational field, 9.8 meters per second squared. So we are pretty dang close. Yeah, somewhere between 5 and 10% error. That is not bad at all. So from our little experiment with a pendulum, asking the question, what affects the period of a pendulum, we discovered it was the length. We found this relationship. Tucked in there, hidden away, was actually the Earth's gravity, the strength of the Earth's gravitational field. That's very interesting. We could theoretically do the same experiment on other planets and try to calculate the little g, the acceleration due to their gravity, the moon's gravity, Jupiter's gravity, something like that, and do the exact same experiment. That would be interesting. So hopefully you guys have a pretty good idea of variables, independent, dependent variables, the purpose of experimentation, hypothesis testing, using graphing to make mathematical models, and then extrapolating some interesting things out of the mathematical model.